Welcome to Under the Microscope. This series is brought to you by the Real Scientists Nano team. Our goal is to provide a platform where scientists can communicate their work and interact with the public.
Hi everyone, today we have with us Otto Mustonen, who is a postdoctoral research associate at the University of Sheffield in the United Kingdom. Hi Otto, how are you doing?
I'm doing very well, thank you very much, and thank you for having me. How are you?
I'm good, excited to know about your science. So let's start with understanding your research. Could you explain your research in super simple words to us, please?
I'm going to give it a go. I'll try.
Okay.
So quantum mechanics is something that describes how atoms and electrons behave, or something that describes how things work on a very small scale.
Mm-hmm.
And the way things work are quite counterintuitive from our normal experience. Mm-hmm. So, for example, if my daughter throws a ball at a wall, that ball is going to bounce back.
True.
If an electron goes against the barrier, there's a chance that the electron just magically appears on the other side, so it goes through the wall.
Mm-hmm.
And that's possible in quantum mechanics, but that's not, of course, if I throw the ball or my daughter throws the ball, it's never going through the wall.
No.
And what I do is I research materials known as quantum materials, mm-hmm. where these really strange laws and peculiarities of the quantum mechanics result in some new and interesting properties and states. Mm-hmm. Often this is because of the way the electrons behave. So the electrons like each other a lot and they interact a lot, and that usually then results in some weird things happening. Mm-hmm. And one example of this that I've studied before are superconductors. And these are materials where if you cool them enough, they lose all of their electrical resistivity.
Okay.
And this happens because the electrons pair up with each other, and then they can move without resistance.
Okay.
So these can then be used, for example, to make a very, very strong magnet, because you can make an electromagnet with no resistivity, so you can put a lot of current through it. Mm-hmm, mm-hmm. So that's one example of a quantum material. Right. What I'm working on right now are something even more complicated. Mm-hmm. Materials called quantum spin liquids. Okay. So these are materials that have these tiny magnets or spins. Mm-hmm. So that is a spin is a magnetic moment of a single electron,
right,
or an ion. And I'm working on materials where in a normal magnetic materials, these spins, or these tiny magnets, below some important temperature, they will freeze and they will all point out in some direction. So they have some rules. For example, in a ferromagnet or something like iron, for example, all of those little tiny magnets will point in the same direction and they'll be happy. Mm-hmm. In some more complicated materials, they'll start to counter each other out a little bit. Mm-hmm. And but usually what happens is that if you just lower the temperature, the spins will become like a solid, so they will all have some symmetry and they will point in some specific direction. And if you heat them up, they'll behave a little bit like a gas. They'll just point in random directions and they're constantly changing. Mm-hmm. But what I'm looking at are materials that behave like a liquid. So okay, something that is still constantly changing, but something that has some short range structure.
Okay.
And these are materials where even if we cool them down, even if we could cool them down to absolute zero, these tiny magnets still wouldn't stop moving. So there, at absolute zero, there is no thermal energy anymore.
Right.
So nothing should be moving.
Right.
But quantum mechanics allows some movement, and so that's movement from the quantum mechanics, not from the thermal energy.
Right.
That
right.
is stopping these materials from freezing. And what one can do with these materials, hopefully one day, is to build a new type of quantum computer. So one could do calculations using these materials.
Right.
And these you can make a bigger and faster quantum computer this way than the normal ones, because you have a material where a lot of these tiny magnets are forming the same state. They are entangled together.
Right. Right. Okay.
And then we can think about what one could do with faster computers. One could improve, for example, one could make better climate models. One could use that for drug discovery. One could use those for finding new materials, using like computational materials discovery, that sort of thing.
Right.
So that's not very simple. That's not these very simple words, but that's what I do.
Okay, I think I understood to a certain extent what you do, and it sounds super cool. It is definitely complicated. It completely goes in the direction, a completely different direction, that the way of thinking or the way of understanding is completely different. So, but I think you did quite a good job of trying to explain it to us, demystify the complicated concepts a little bit. And I hope you will also do that when you're taking over the account, which brings me to the next question. What can the followers expect in the week that you will curate the Real San Anno Twitter account?
So I'll be talking about quantum materials in general. I'll be explaining some general concepts. There are some reviews that are coming up that I'm going to talk about that could be of interest. And then the other thing I'll talk about are these experiments that I do on the materials. So I do a lot of experiments at large facilities using tiny particles called neutrons that are at the core of atoms.
Right.
And there are a lot of things that can be done with those. So I'm going to explain how to run, how it all works, how to run experiments, and to give some advice if someone hears it and thinks like, hey, I could use that in my research. I'll talk a little bit about how to actually get to do those. So these are experiments that are quite expensive to run, but luckily we don't have to pay for it ourselves. But we do have to convince somebody else to let us measure because it's expensive.
Right. So that's a very, very important piece of advice, or pieces of advice that you will be giving if one wants to do these expensive experiments. How to convince other people. You have experience there. Okay, super. So that sounds like a super action-packed week. Looking forward to your time on Twitter, and thank you very much for speaking with me.
It's a pleasure. Thank you for this opportunity.
Thank you for listening. To know more about us, please visit our website, realscientistsnano.org, and follow us on Twitter at realsci_nano.